Okay, so now we are into chapter 15, other regression models. So we are now going to move off of simple and linear. If you don't have a simple, then it is a multiple linear regression model, and things don't have to be linear. So we could have categorical variables, or we could have curvilinear regression, or we will need transformations, which means that we somehow things are relationship is not linear, but if we do something, we can make it linear. And then outliers, what to do with when you find some points which are not following the model, and then common mistakes. So the simplest thing to do first is to just have more than one variable. And if you have more than one variable, basically you have more than one parameter, and the model becomes y equal to b0 plus b1 x1 plus b2 x2 and bk xk. So there are k predictors here, x1 through xk. And so therefore there are k plus 1 parameters, b0 through bk, and then there is an error term, right? And so when you have predictor, so k predictors, that means you will have n observations of each of them. So you will have first observation will consist of a vector, right, with y1 and then all the predictors. Second observation will be another vector, and so on and so forth. So everything that we did before in what we call scalar variables, now we will do it in vector variables and matrix manipulation. Alright, so you can write down the whole equation. Y1 is equal to this, y2 equal to that, and yn equal to this, and then the whole thing can be written in a matrix form. In a matrix form, y is equal to this matrix times b plus e. Alright, so y equal to x times b plus e, where x is the matrix, b is a vector, y is a vector, e is a vector. Basically everything is a vector, some have one column or one row. So, that's all. But now this model looks very familiar. If y equal to xb plus e, this is like our simple linear regression, except that everything is a matrix here. Alright, and so we can actually determine best value of e that minimizes the error squares, and then compute the values. So let's first start with computing the value. So now in our previous example that we had for CPU time and disk IOs, we add memory size, second variable. So now we have y as a function of two variables, and we can write down the vector x. So the first column is always 1 in that x vector, if you remember. Then this is x1 and this is x2. And when you want to take a square of any matrix, all you do is you transpose it and multiply. So the square, basically x transpose x is this value. You take this, transpose it, and multiply. Everybody remembers the multiplication, matrix multiplication, and so you get that. You take the inverse of that matrix, you get C, and then you multiply the transpose of with y, you get that. And so the b value, actually the book, the formula is in the book, so I didn't put the formula in the slide here. So anyway, if you look in the book, you will find that the regression parameters are x transpose x inverse x transpose y. So we calculated this part first, we did the inverse, and then we calculated this part, and then we multiply these two to get this vector. And therefore the regression equation is simply CPU time is b0 plus b1 times x1 plus b2 times x2. Now using those B values we can calculate the errors as before. So this is the measured value, this is the predicted value from the model. The difference between those two is this error value, and then a square of the error is this column. So we make this column and we add up. Obviously the error should add up to 0. Alright, and the error squares is what we are concerned about. That should be as small as possible. So this is called sum of squared errors, which in this case SSE is 5.3. We have SSY, which is right here, and we have sigma, all of those things, so we can use that in the formula for SS. So SSY, SSE can be calculated individually as we did in the table before, or it can be calculated as a matrix as given here. SSY is that value, SS0 is simply the sum of the mean squares, and the formula is that SST, the total squares of y, the total square is equal to SSY minus SS0. If you take the difference of those two, that is the unknown, and that is equal to, sorry, what happened here? Page up. The sum of squares reduction due to regression is equal to SST minus SSE. So the total sum of squares is 205. But after we fit the model, the errors have total sum of squares of 5.3. So the model explained 200 out of 205. Alright, that measures the goodness of the model, that it explained 200 out of 205, which is like 97% of the variation, right? And so the R square is whatever is explained by the regression divided by the total. And so the regression explains 97%, the multiple correlation. So this is called the coefficient of multiple correlation, not correlation. Why? Because now it is not correlation between y and x1 or x2 or x3, it is with all of them. So that is just the multiple correlation, square root of r square. And the standard deviation of errors is, now this is an interesting formula. The standard deviation of error is SSE divided by n minus 3. Why n minus 3? Anybody? Can you guess where the 3 came from? Everybody should be able to guess where the 3 came from. Yeah.
It's definitely the degrees of freedom is what's
yeah. So why the errors have n minus 3 degrees of freedom? Yeah. Why the errors have 3 degrees of freedom? N minus 3 degrees of freedom. Because how many parameters have we estimated from the model? 3. Right? If we had k variables, how many parameters would we estimate from the model? K plus 1. Right? Here we have 2 variables predictors. We estimated 3. When we had 1 before, in the previous one, we estimated 2. Right? So the errors had n minus 2 degrees of freedom. Now we are estimating 3. So n minus 3. If you have k variables, you are estimating k plus 1. So the errors, the degrees of freedom is n minus k minus 1.
So this means that the more variables we have to take more observations in order to get more accurate results.
Right, exactly. You basically, because now the degrees of freedom are getting less and less, so the SE will go up if you put a lower value here. So the standard deviation of error is this now. Okay? And now everything else that we talked about before goes, which basically we can have a standard deviation of B0, B1 and B2. Each of them have formula. Each of them have degrees of freedom, which is same as the error degrees of freedom. And then therefore each of them have a confidence interval, which you can calculate using the degrees of freedom and the standard deviation. Okay. And interestingly enough, now that we have overfit the model, we find that all parameters are 0. The previous model was better. For the same data, when we had only one variable predictor, we had non-zero values. But now with 2, we have increased the confusion. Okay? So that is another common mistake people do, is that they put everything into the bucket and they say, look, I have taken care of everything in the world. Alright? You have just lost everything that was there before by putting too many things. And because they don't do confidence intervals, they will not even recognize that this is what is happening. They will just put this formula and that's the end of that analysis. Alright, so now you know why you need the confidence intervals to really recognize whether really the model is any better or good. Now, interestingly enough, you can do the same thing for the predictions. So you have predictions which have a mean, which have a standard deviation, and which have a confidence intervals. Okay, I hope everybody understands. I mean, basically there are formulas here for a single observation and for infinite observations. And similarly, there must be a formula for m observations, which I didn't put here, but basically it would be 1 upon m somewhere. And so you can calculate the confidence intervals for those. Alright. So what we have done so far is we just extended the single variable simple linear regression to now 2 variables in this example, but basically you can easily do this for the k variables. And we repeat everything. We haven't repeated the visual test, but you need to do those visual tests exactly as before. And you will probably do that in the exercises at homeworks. But same thing applies. Assumptions are all same. Okay. And so let's go through something called analysis of variance, generally called ANOVA. 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 So basically the total sum of squares is equal to sum of y minus SS0 or SSR plus SSE. So whatever is explained by the regression and whatever is not explained by the regression, that is equal to the total. Right, in terms of degrees of freedom, n minus 1 equal to k times n minus k minus 1. Okay, so the assumptions are that errors are IID, normal, and that means Y's are normally distributed. X are non-stochastic, and the various sums of squares have a chi-square distribution, blah blah blah. Anyway, so now let me just explain this chi-square thing. That's the new term. So there are many distributions, and chapter 29 in the book explains all the distributions alphabetically. But we have already introduced normal and t-distribution, but chi is basically the sum of normal squares. So if you take one normal and take another normal, You square it and add them, you get a chi-square distribution. You take third one, you add it, chi-square distribution. So chi-square distribution is basically sum of n squared normals. If you just take excuse me, if you just take n normals, you sum them up, what do you get? Normal. If you square them and then add them up, you get a chi-square. Okay? And if you take a chi-square and you take another chi-square, you divide them, the ratio has an F distribution. Okay? Again, if you go back to the book, chapter 29 has a nice table which I have shown you before, and you can see it again. Page 501. 500. Okay. On page 500, there is a figure 29.1 and 29.2. So look in 29.2, it says normal. If you add them up, it says sigma x, it goes back to the same normal. Okay? If you do x1 upon x2, which means you take two normals and take a ratio of them, it becomes Cauchy distribution. If you take a log, it becomes a log normal distribution. If you take a square, the arrow going to the right, it says chi-square. Right? And then under chi-square, if you take the sum of chi-square, it remains chi-square. If you take chi-square and divide by another chi-square, you get an F. You take an F and you take a square root of that, you get a T. Okay? And if you take a normal and you divide by chi-square square root, you get a T. If you understand these relationships, then you will understand why did we use the T distribution before. And the reason I am bringing it up again is because I am going to use now F distribution quite a bit. Okay? And the reason we are going to use F distribution is because we are going to take chi-square and divide the chi-square. So, first of all these sums of a square, what distribution they have? Huh? No. Variables have normal. Sum of squares of normal has chi-square. So all the sum of square, whether we say SST, SSE, SSR, SSA, all of them have chi-square distribution. So when we start taking the ratio of these sums of squares, suppose I divide SSE by SSY or something, okay, or SSSR by SSY. When we take the ratio, that ratio will have a distribution which is F distribution. So now let's talk about that. Alright, given SSI and SSJ with VI and VJ degrees are nu I actually, nu I and nu j degrees of freedom, the ratios have F distribution with n nu I numerator degrees and nu j denominator degrees. So F distribution has two parameters. What is the numerator degrees and what is the denominator degrees of freedom. So whatever ratio we divide, we have to know that, and then we can do the test. So the test that the one sum is less than or equal to the second one is basically you can do the F test. And what you have to do is you have to take the ratio and then you have to see whether it is less than or equal to the F value which is given in the book. So the F table is another table which is page 634 and 635 and 636. Three. There are three F tables. One is for 90%, one is for 95%, and one is for 99%. So let's just take the first one, which is 90%. And the way you read this table is that you have a numerator degrees of freedom and the denominator degrees of freedom. And so you look at the numerator degrees and denominator degrees, and then you find the value right there, and then you compare that with the ratio that you are trying to compare. And so I will show, the example will make it much more clearer, but we will take several different ratios. So first we take the ratio, we take the sum of a square and divide by its degree of freedom. So we noticed that SSR had k degrees of freedom and SSE had n minus k minus 1 degrees of freedom. So we divide SSE by that and SSR by that. And if we take the ratio of these two, by the way, these are called mean squared by regression and mean squares due to errors, right? If we take the ratio, then it has fk, comma, n minus k minus 1 degrees of freedom. This is the numerator, this is the denominator. And if this ratio is, if MSR to MSE is very small, that means that the model is no good. We could have set all the parameters to 0 and this will be all right. So that's what we want to see. We want to see that the ratio is kind of high. The part which is mean square due to regression is much higher than the mean square due to errors. Okay? All right. So now let's just skip the rest of it actually. This is what is important is to do this kind of table. So basically what happens is when we do an analysis of variance, ANOVA, we make a table like this. And in this table, first line is y. And second column in that row is SSY, total sum of squares of y. And the degree of freedom is n. The second column is by bar, which is the mean of y. Second column is sum of squares of by bars, so and it has 1 degree of freedom. Third column is the ratio. Third row is the difference of the first two, so y minus y bar, and sum of squares is simply the ratio and the difference of these two, and the degree of freedom is n minus 1, the difference between those two. And we write down 100% variation. This is the total variation that we need to explain. Then we write down the regression. The regression is SSR equal to SST minus SSE. So before we can compute that, we have to compute SSE. So we go to the next row, errors, and we put down the SSE value there by whatever we computed from the tables. Then we can compute SSR. Once we know SSR, we can take the ratio, and that tells me what percentage of the variation is explained by the regression and what percentage is errors. If we divide by the degrees of freedom, we get the mean squared errors and mean squared ratio. And if we take the ratio of those two, then we can compare that with the F value in the table to figure out whether this ratio is too high or too low. So I think the best thing is to do an example. So the example that we just computed, the CPU disk memory example, for that example, the sum of squares of y is 828. And sum of y bar squares is 622, so the only unexplained variation is basically the real variation is 206. It was 205 point something before, right? That's what it is. The errors have a ratio of errors have the sum of 5.32, and therefore the regression explains the difference between those two, which is 200 now. 206 minus, it was 205 something here, and minus 5 point something is 200 point something. Anyway, so this is 100%, 206. This is 2.6%. And so the regression explains 97.4%. So this is basically R squared right there. Now we write down the degrees of freedom. We divide by the degrees of freedom and we get the mean squares. So mean squares here is 100. 200 divided by 2 is 100. And 5.32 divided by 4 is 1.33. This is mean squared errors. We take the ratio of those two. Our F value comes out 75.40. And the F table says that it should be more than 4, so it is more than 4, so that says the model is good. Right? Huh? To get 4.32. So let's just look at 4.32. How did we get 4.32? So first of all, before I go to the table, we take this is a ratio of two variables. One, the numerator has a degrees of freedom 2, and the denominator has degrees of freedom 4. So when we go to the F table, we look at table A, 0.6, 90 degrees of freedom, and we look at the numerator is 2, so we look at the second column, and the fourth row is 4.32. Right? So that is the theoretical value, and ours is better. By the way, we can also take a square root of this value, this MSE, and we can get the standard deviation of error right there. All right. So now here is a dilemma. Regression passes the F test. So all the parameters cannot be 0, but we just saw that none of them, all of the parameters we saw B0, B1, B3, their confidence intervals were 0, included 0. Right? So while each one of them is 0, but all of them pass the test together, what's the problem? This is a statistical, basically, error problem. It's called problem of multicollinearity. Is that this kind of contradiction comes in when you put too many variables into the model. Okay, and now you're getting two different results. On one side, one test says good, other test says bad, and that's all because of putting too many variables. Okay, I think I will stop right here, and we'll discuss more of this problem next time.